In this video, I'll go through the solutions to the quiz we did on functions. So we'll start with this one here. The function f from negative infinity to b with this rule here, k value greater than 0, we'll have an inverse function provided that. Okay, so the first move I'm going to make is try to work out what this function looks like. Because basically what I want to do is, with a domain restriction, make the function 1, 2, 1. All right, so the way I'll do it is I'll grab that. And what I can see is that we're going to have x equals 0 and x equals plus or minus root k as our intercepts. All right, so it's going to be negative root k, and turning point there. Now it is a negative quartic, so what's going to happen is it's going to come through like this and go like that. All right, so we can see here that it's from negative infinity to b. So we're coming in from negative infinity, and what we need to do is stop at this point here. Whatever this point here is, we want to know what that value is, and that's going to give us a one-to-one function. So to do it, I would slam this one out on the calculator. So I'm going to say define f of x equals k times x squared, take away x to the 4. Then what I'll do is get the derivative of that, so shift minus d dx f of x. Then what I'm going to do is, I think I'll just get the x value of the turning point. So I'm going to do a solve, and c equals 0 for x. And what we've got here is, we're interested in this value here. So negative root 2k over 2. That's the one that will be this x value here. So that's going to be that x value. So we can see that I think it's this one here, provided that b is less than root k on 2. Now we'll just quickly test that. K over 2 equals negative root k over root 2 times root 2 on root 2 means that we've got negative 2k over 2. All right, so that's correct. So it's going to be response A. So anything larger than that, or it could be smaller than that. No, it didn't give it as an option. Yeah, so it has to be that one there. None of these other options, like this one here, B is less than K. Well, K, where is K going to be? Somewhere over here. You can see that basically, oh no, K is going to be up here somewhere, because this is the square root of K. So K will be up here. And we can see that really, if we restrict it below K, it's certainly not going to be one-to-one. And it will be the same for all of these options except for this one here. Okay, this one here, consider the function with the rule f of x equals that, where that, then the function and its inverse do not intersect. Okay, so this is a hyperbola. So for hyperbolas not to intersect, we'd have to have something like that. But we've got an a value here which will move the hyperbola around, so I don't think so. We'll intersect at only one point. Well, if they're going to intersect, they'll probably intersect at least 2, right? So we'll probably get something like that if that's the case. So I doubt this is correct. 3, can't see that happening. Don't know how it's going to intersect 3 times. Have an infinite number of points of intersection. That's interesting. And intersect at only 2 points, 0, 0, and 2, 2, when a is equal to 0. All right, so I think the way we'll do this one is we'll just get the inverse, and we'll see if the calculator will give us an inverse. So we'll go define f of x equals control divide x take a over x take 1. Okay, so the way I like to inverse is I just go solve f of y equals x, so that's swap x and y, and solve for y. And what you can see is the function and the inverse are exactly the same. And if they're exactly the same, then basically what it's doing is it's going to, how to explain this? If the function and its inverse, so just say this is our original function and our inverse is exactly the same as this, it's going to run directly on top of it, which means that we're going to have an infinite number of points of intersection. And I suppose the way to think about it is a bit like linear functions. You know, if I said to you, I've got a function y equals 2x plus 3, where does it intersect the function y equals 2x plus 3? You'd go, well, infinitely many places. So I suppose that is the kind of thing that explains that one. All right, here we go. So question 3. The function will have an inverse for... All right, so these ones here, can't really work it out until I actually have a look at what the function looks like. So it's a cubic function, it's a positive cubic, so it's probably going to look something like that. Now, the best way to do it is, again, we'll define it on the calculator. So define f of x equals 5x to the 3 plus 10x squared plus 1. Then what we'll do is we'll solve f of x equals 0 for x. Only one intersection. Alright. So at -2, whatever it is, around about there, it'll go through the x-axis. So I'm anticipating that it's going to go, I don't know, something like that maybe. Okay. So what we'll do is get this turning point. So we'll get a derivative, shift minus d dx f of x, solve that, ans equals 0 for x. Okay, so stationary points at -1 and 1/3 and 0. Okay, so it turns on the axes. All right, so that's important to know. So I'm going to redraw my graph. So that happens, where's the rubber? There. Okay, so what's going to happen is it's sort of going to come up through there, turn, and then turn on the axis itself. All right, now what can we see here? So we can see it's 1 to 1. Like, I'm just looking at option D here, right? E rather, 0 to positive infinity. That definitely is 1 to 1. So I reckon the answer is D. Let's have a look at some of the others. Negative infinity to -1. Well, no way, because here's negative infinity comes up, and here's -1 1/3, and it's coming down. Okay, so here would be, say, -1, and we can see here that it fails the horizontal line test. So that's why that can't be right. Negative infinity to 1/2, I mean, no way, right? It goes up, down, and then up again, right? So that can't be right. -2 to positive infinity, well, here's -2, positive infinity. We can see it goes up and down and up again, so no way, and definitely not all reals. Okay, so yeah, it's definitely 0 to positive infinity. All right, let f of x be that, and g be the inverse function. Given that f of 0 equals 1, what is the value of g dash 1? Okay, so we define f of x equal, actually, I think what we'll do is we'll just put in f of 0 equals 1, and I think that's going to give us the b value. So f of 0 equals b to the 5 equals 1. Okay, so we know that that is that, which is 1. B equals 1 to the, so the 5th root of 1 which is just 1. Okay, so our function is f of x equals ax plus 1 to the 5. So I think what we'll do is we'll get the inverse function, derive the inverse function, and then just do g dash 1. Okay, so define f of x equals a times x plus 1 to the 5. So same, we'll do solve f of y equals x for y. Okay, there is our inverse, and then we've got to get a derivative, and then we're going to slam in 1. So shift minus d dx, this thing, with x equal 1. There we go. Alright, how do you do that without a calculator? Wouldn't have a clue. Let f and g be functions such that this is the case, the value of that. So f of negative 1 is 4, so that's g of 4, and g of 4 is 6. Alright. The maximum value of this over the domain 0 to 2 is, okay, so think there's a couple of ways of doing this. Let's just try a couple. So what I'll do is define f of x equal, what's the function? X take 2 times e to the x with 0 less than equal to x less than equal to 2, I think. Yeah, 2. Okay, so there it is over that domain. So now I think we can just run an fmax on this. Let's just try that. So we'll do some calculus and go function maximum. So fmax asks for the function, the variable, the lower value, and the highest value. And what that will do is just pump out the maximum value over that domain, x equal 2. So they're saying that the highest value of that function is at 2. The maximum value. Okay, so what we'll do then is that's the x value for which it occurs. So then I think what we'll do is just put that into the function f of 2. So what fmax does is it returns the x value of the of where the highest value occurs. It won't actually find the value for you, so you have to go get it yourself. So the highest value is going to be 0, and remember that occurs at x equal 2. The other way you could do this is probably graphically. So control doc graphs, graph f of x, which we've already restricted the domain. And you can see really quickly there that the highest value is going to be 0. Okay, so that would have been probably a little easier. You can just be sure about it by going analyze graph for a maximum. You can see that it occurs there. What value does it occur at? Negative 0.000, effectively 0. Okay. Okay, so we've got a linear and a quadratic. So if h is the composite function given by this, so they want us to compose the function and then restrict the domain of the function. So let's just make the composition. So it's f of, now g of x is x plus 2. So it's x plus 2 all squared, take away 4. So that is our composite function. Now it goes from negative 5, here's negative 5, to negative 1. Now what we can do, we can see here that they've given us the turning point when we form the composition. So it's going to be at negative 2, comma, negative 4. All right, so we can see that the lowest value is going to be at -4 inclusive. So that's going to be the range. So the lowest value has to be -4. So I'm not even really worried about what the highest value is because the lowest value is guaranteed to be this one here. So this would be incorrect because it wouldn't include the turning point. And yeah, the rest of them just, well, don't work. Okay, oh, this one was hard. Consider the functions defined on their domains. Okay, the maximal domain of f of x take away g of x. So this function here is the standard root function moved 3 to the left, so it's that. This one here is moved a to the left. All right, so here's a, or a to the right rather. So here's a and here's -3. All right, so we can see that in this instance here that f of x take away g of x is going to be these values here. Okay, so because this function here produces a value and this function here produces a value. Below these values here, it doesn't, so we can't subtract the functions. Okay, so basically from here we'll say that it's going to be so the maximal domain is going to be a to positive infinity inclusive of the point because the function exists there and it exists there. So it's a to positive infinity. Now we got that anywhere? If a is greater than -3. Yeah, so if a is greater than -3, then what's going to happen is like there's greater than -3, there's greater than -3. So it's got to be whatever the value of a is onwards. All right, so this is the only one that makes that true. Now this is also going to be true because what happens is if we move the a value down to say here, if a is less than or equal to -3, all right, what's going to happen is the domain is going to be -3 to positive infinity because again we've got -3 and we've got the function. All right, so we can add them together there. So it's going to be this part as well. So here is our correct answer, E. All right, we didn't include this one here, but what they want is the range of the function, so I'll do it anyway. So you just need to know something about the standard log function. So the standard log function looks like this. The rule on logs is you can't log a negative number, but what this function does here is if you feed it a negative number, it turns it into a positive number. So actually what this function will look like is something like that. Now you could graph that onto the calculator. In fact, we might as well do it. So we'll go control doc graphs and we'll ask it to graph ln x squared. So there it is there. All right, so they want the range of this. So from -1/2 to 0. So from like somewhere here, -1/2 to 0. Union with 0 to +2. So 0 to +2. So we can see that the highest value it's going to pump out is when x is 2. So we can see that that's the highest. And the lowest value it's going to produce is going to be what? It's going to be -infinity because we get infinitely close to 0 on either side. All right, so let's just try it. Control and doc, calculator, define f of x equals ln x squared. So if I put in 2, f of 2, let's get the decimal approximation, 1.3. Put in f of -1/2. That's interesting. F of -1/2 is the same value. Why? Anyway, I'm not going to worry about that for the moment. So I can see that or they're equally as high, but the 2 produces that value itself. Okay, so it's definitely going to be at 2. So the highest value is when x is equal to 2. which is log E4, or this one here, which is, I will rewrite that as log E2 to the 2, which would then be written as log 2 log E2 using that log law. So that's the highest value it can pump out. Now let's get infinitely close to 0. So I'm going to put in f of 0.00001. What this should do is produce a really low negative number. Well, not really low, but negative 41. And the lower the value I go, you can see here 0.0000000000001. It's just going to get lower and lower and lower the closer I get to 0. So basically we're going to say that it is from negative infinity up to 2 log E2. So yeah. All right, so let's finish that off, negative, and we don't include negative infinity obviously. So some tough ones in there for sure.